So in this lecture, why don't we get started and understand a little bit about Einstein's general theory of relativity. And let's talk about its foundation. Now, to set the stage, recall that Einstein's special theory of relativity, which was published in 1905, describes the transformation between inertial frames with a constant relative velocity between them. Remember, that was a requirement. But we can ask, well, what about transformations between frames that do have a relative acceleration? Now, there's a reason we assume that in special relativity. A frame that undergoes acceleration feels the effects of the force that causes that acceleration, i.e. Newton's second law. So one can definitely distinguish whether you're in a frame that's moving at a constant velocity versus one that's undergoing acceleration. Right? If you're one undergoing acceleration, like an elevator that accelerates upward, you feel the effects of that force. So the symmetry between these two reference frames, one that's at a constant velocity and one that's accelerating, is broken. You can tell the difference. Nevertheless, we can try to incorporate the physics of such accelerating frames. And in fact, accommodating accelerating frames, as well as including the force of gravity, is the subject of Einstein's general theory of relativity, which was published a bit later, back, in 1916. And in constructing this general theory, it will, of course, also include special relativity within it. So special theory of relativity is basically a special case, if you like, of the general theory of relativity, which can accommodate also accelerating frames and gravity, a new fundamental force to consider. Now, the heart of the general theory of relativity is something called the principle of equivalence. So let's understand what we mean by that. In a nutshell, the equivalence principle says this, that there is no experiment done in a small confined space which can tell the difference between a uniform gravitational field and an equivalent acceleration. Now, what do I mean by that? Imagine you're in an enclosed box, an elevator-sized box, and you're standing inside of it on the surface of the Earth. You feel your weight. You're pushing on the ground pushes up on you. Now, perhaps you were in space, in orbit, I should say, with not necessarily feeling any effects of gravitation, but your enclosed box begins to accelerate. Maybe a rocket thruster fires. And you will feel the acceleration, the force that causes that acceleration. Now, if you're in this enclosed box and can't see out any windows, could you tell the difference? The equivalence principle says you cannot. Now, the heart of this equivalence principle is that the so-called inertial mass, let's call it MI, that relates acceleration of an object under the influence of any force in F equals ma, and the gravitational charge, let's call mg, in Newton's law of gravitation here, right? F is big G times the product of the masses over the distance squared between them. So say you're near the Earth with mass capital M, you have gravitational mass mg. The force between you and the Earth is given by Newton's law of gravitation here. But that also causes you to undergo some acceleration, right, by Newton's second law, F equals mia. Your mass times acceleration. And we're essentially saying, can we tell the difference between the mass in F equals ma and the mass in the law of gravitation? We can contrast and see why that's a little bit of a profound statement. Let's talk about the electric force, right, in Coulomb's law, right? The force between two electric charges, one with charge Q1 and one with charge Q2, is the product of the charges over 4 pi epsilon naught, basically electric permittivity constant, over the distance squared between those charges, where Q is the electric charge. Right? The mass didn't come in at all. Right? But somehow mass is coming in for the force law for gravity. And they're apparently the same. And if they are exactly the same, and actually measurements tell us that they are so to a very high degree of precision, as precisely as we can measure, then there really is no way to tell the difference between an accelerating frame, one that we feel a force feel the force that's causing the acceleration by F equals ma, and just say the force due to gravity. We can't tell the difference. It's the same mass. So whether you're in a rocket in empty space accelerating at 9.8 meters per second squared, or you're standing here on the Earth where the acceleration due to gravity is 9.8 meters per second squared, you can't tell the difference. That's the heart of the equivalence principle. And that has some profound implications. In particular, turns out that means gravity can bend light. Now let's understand how we can understand that concept by using this equivalence between gravitation and an equivalent acceleration. So let's consider a rocket that undergoes constant acceleration a. Right? And we can imagine a light beam coming from the left and crossing through, maybe it's going through some windows in the rocket. So light enters one side, but as the rocket is accelerating upward, it'll appear to someone within the rocket as if the light is falling in the reference frame of that rocket, that accelerating reference frame. It takes the rocket a finite amount of time, in fact, for it to, it takes the light, I should say, a finite amount of time to cross the rocket as rocket's accelerating across that light beam. So here's my light beam. It's crossing the rocket as it's accelerating upward. There's a finite amount of time for it to cross the rocket. And we can ask, well, what does it look like inside the rocket's rest frame where the astronauts are? Right? Well, I claim the trajectory will be a parabola for constant acceleration. And in their frame here, if we draw a box, this is that box that the astronauts are in, it will look like light here is coming in and falling just as if you had tossed a stone and it fell under the influence of gravity, just because the rocket itself is accelerating upward as the light beam crosses. So we're kind of talking two frames here, right? We have this astronaut frame, the accelerating frame, but we also have a frame outside of the rocket. Perhaps we're here on the surface of the Earth, and we're the ones that shot the light beam that went in a straight line across the rocket. So in that frame of the Earth, we saw this light beam just go horizontally, but in the frame of that accelerating rocket, it looks like light fell. It bent downward. Okay, we can ask, well, how much does light bend as it crosses that accelerating frame? So let's give the width of this rocket a length L, and the amount that that rocket will move vertically in the y direction, let's say, in some time t at a constant acceleration a is 1/2 at squared, right? You've learned that in physics 1. So how long does it take the light to cross a distance L for that horizontal width of the reference frame? Well, essentially, if the deflection is small here, so this parabola is just essentially nearly a straight line, that would just be the length divided by the velocity, which is the velocity of light. So L over c would be the time for the light beam to cross the enclosed compartment of that rocket if the deflection is rather small. Otherwise, we can do it more mathematically correct and work out the curvature there. But let's not do that right now. Let's assume that the deflection is small. So it's L over c for time. We can plug that into 1/2 at squared and see how much the rocket has moved in the time for the light beam to cross the rocket. That's 1/2 at squared, as we said, but plugging in that t is L over c, it's 1/2 a L squared over c squared. Now we can use the equivalence principle and set the acceleration here, a, to be g, the acceleration due to gravity on the Earth's surface. And we can ask, well, okay, given some length L, how far does the rocket move, or equivalently, how far does the light beam fall down vertically in the time it crosses the length L? Well, as I was hinting at, it's going to be small. So let's take a really, really large distance. Let's take 3,000 kilometers here. Right? So it's approximately the size of a continent. And if we put that in for length, and we have that the time to cross was L over c, 3,000 kilometers over the speed of light, and the speed of light is 3 times 10 to the 8th meters per second, that's a short time. It turns out the amount of time here, the amount of distance light falls is only 0.5 millimeter, even over the length of a continent, right? So it is very tiny for g of 9.8 meters per second squared. It's a small amount. So it's not much in Earth's field, all right? But nevertheless, you can see and measure such effects if we start to consider more, if you like, larger astrophysical objects. So although the bending of light is small near Earth's gravitational field, it is larger when it passes by stars and other massive objects. For example, when light passes by our sun, the bending can be measurable, at least during an eclipse, right? We need the moon to block the light of the sun. Then we can see the night sky in a total solar eclipse, and we can see stars that are near the sun. And in fact, if this equivalence principle is correct, and Einstein's general theory is correct, light should bend if that light passes close to a massive object like our sun. And in fact, this was a prediction of Einstein from his general theory. He tried to predict how much starlight would bend as it passed near the sun. And right after he released his theory in 1916, there was an expedition mounted to measure such an effect in 1919, where they measured a deflection of 1.75 arc seconds. So a very small angular displacement, but nevertheless was measurable, and it was in complete accord with the general theory of relativity. And essentially what we're talking about here is that gravity bends light even though photons are massless. So, right, we've learned that the photons that light is quantized into are massless. So in Newtonian gravitation, they should have no force of gravity. In fact, through the general theory of relativity, equating it to accelerating frames, light does bend. And we can illustrate here that by this diagram. So we have the Earth down here, the sun, and say a star whose light normally would be blocked by the sun. And okay, let's imagine right between the Earth and the sun, well, closer to the Earth, of course, is the moon, so it blocks out the sunlight, but we can see light around the field of view of the sun, which has been blocked out by an eclipse. So the starlight, which comes from the star here, will form a curved trajectory as it bends in the gravitational field of our sun. And to us, if we just look at where the starlight looks in the night sky, we'll follow a line, and we'll say, it's somewhere over here, even though the star was a bit displaced from there. And if we move the sun away on a different night, then we would actually have pointed out that the starlight was at this angle. So there's some angular displacement theta, which for this eclipse was only 1.7 seconds of arc. All right, so that was a very important prediction that was verified and gave wide acclaim to this general theory of relativity of Einstein. But we can have even more extreme bending of light. For example, around a black hole. Now, this image here is a simulation. It's the simulation of the bending of light from a so-called accretion disk around a black hole. And this comes from the movie Interstellar, where the black hole was named Gargantua. And it gives you this interesting shape. It looks like an eye looking at you. Now, in fact, on the horizontal plane is that disk. There's a disk of dust and material orbiting the black hole, which is falling in. It's inspiraling, and that's why it starts to glow. But why does it make this circular shape around it? Well, that's from the bending of light by this enormously powerful, strong gravitational field. And I can consider it like the disk around it, like the disk around, say, a planet Saturn. But the mass is so much for the black hole. It is bending light that would have gone, say, vertically up from the horizontal disk. But the light has bent due to the gravitational field and comes toward the observer. So you see light not only in this horizontal plane coming toward you, right, but you see light from in front of you and behind in front of the black hole and behind the black hole, bending around and coming toward the observer as well. And that gives you can see all around the black hole, in other words. You see the disk, which should have been the horizontal plane, looks also like in the vertical plane. So pretty cool. Now, something that is real, this is a simulation, but actually done and computed accurately according to the full theory of general relativity. So there's nothing wrong with it, just we've not imaged precisely that, although we have started to approach imaging the material around black holes. But we can talk about other real images, and we can talk about the phenomenon known as gravitational lensing. So let's look deep into the universe. And if you look deep into the universe, you'll see lots and lots of galaxies, a huge number of galaxies. But if you look in this image here, from the Hubble Space Telescope, you'll see some distortion. Some galaxies look very stretched out, right? They look like wisps of string or something like that. What's going on there? Well, basically there is matter between us on Earth and those distant galaxies. And that matter also can bend the light. And it acts a bit like a lens. Right? It's just like we saw the light around this simulation of a black hole. We're seeing this light bend and focus. And it can take, say, a very small disk-like image, say, of a galaxy and distort it, for example, into these filaments that you see in the image here to the left. And in fact, we can invert that. We can use the equations of general relativity and where we can determine how much bending there was and adjust the mass between us and that distant galaxy to match what we see. And that allows us then to estimate how much mass lies between us and that distant galaxy. And that can be used then to measure mass in the universe. But the relationship here is that bending of light, which is called gravitational lensing. But we've turned that around now, assuming now that obviously general relativity is verified, we can start to measure mass. And there's some interesting conclusions that come out from this type of measurement as well as many other types of measurements, which is there seems to be more mass in the universe than accounted for by the bright galaxies and stars that are out there. There seems to be dark matter around the universe. It is bending light, but we can't see that mass directly. So very interesting, but that's a different story. Okay, that ends this first lecture on general relativity and the equivalence principle.